Alright, in this video I'm going to be introducing you to matrix methods, so techniques for solving linear algebraic equations. In the last video I talked about how we could take sets of linear equations and write them in matrix form, and now we're going to talk about solving them. So remember, we talked about the example of three equations with three unknowns. Here I've written just kind of a general case. So I've written the coefficients out as these A11, A12. They actually correspond to the components of the coefficient matrix that they correspond to. So if we have three equations with variables x1, x2, and x3, those are our unknowns. Everything else is a known, and it's a constant, some scalar value. Now we can write that in matrix form like this. Now, why is this useful? Why would we want to do this? So in engineering, we often run into problems that result in sets of linear equations, and we can formulate them and format them into matrix problems. And so matrix methods for solving matrix problems become a very efficient and useful technique for solving such engineering and scientific problems in general. So that's why we want to study them. I want to go ahead and review some matrix terminology that I'm going to be using in future videos, and so that you can have a working understanding of what I'm talking about. So there are some special matrices that you should know about. Probably the most important of these special matrices is the identity matrix. It has ones along the diagonal and zeros everywhere else. The more general, just diagonal matrix means that it's not necessarily ones, but the only thing that's non-zero is the main diagonal. Now, a symmetric matrix is one that everything above the diagonal is a mirror image of everything below the diagonal. So see here, everything above the diagonal, -5, 7, and 1, is mirrored down here, -5, 7, and 1. So we can write that compactly by saying the ith row and jth column of the matrix is equal to the jth row and the ith column component. It's a compact way to write it. Some other matrices are lower and upper triangular matrices. So if everything above the diagonal is 0, we call that a lower triangular matrix. Whereas if everything below the diagonal is 0, we call it an upper triangular matrix. So in general, when we're talking about matrix algebra, if we take two matrices and add them together, we just take the resulting matrix is of the same size as A and B, and each component is just the sum of the components of A and B. Likewise for subtraction. Now we can also take matrices and multiply them by a scalar. All we do is we multiply each component in the matrix by the scalar value. So here I've got 12, 4, 5, and 6 as the components of my matrix. If I multiply them all by 3, I get 12 times 3, which is 36, 3 times 4, which is 12, 3 times 15, 3 times 5, which is 15, and 3 times 6, which is 18. Alright, so that's how we do multiplication by a scalar. Then there's matrix multiplication, which is a little bit more complex, but pretty simple. If you're not familiar with it, go back and watch my video on matrix multiplication. Alright, we also need to talk about the matrix inverse. So the inverse of a scalar or a number is just 1 over that number, so that when you multiply a number by its inverse, you get 1, which is shown here. Well, the inverse of a matrix does the same thing. So if you multiply some matrix A by its inverse, the inverse here is denoted by raising it to the -1 power, it doesn't actually mean that you raise each element to the -1 power. This is just the notation for saying this matrix right here is the inverse matrix of A. It doesn't mean raise everything to the -1 power. When you multiply A by A inverse, you get the identity matrix. Okay, so A times its inverse equals the identity, or the inverse times A is also equal to the identity matrix. Alright, now let's talk about solving sets of linear equations using matrices. Alright, in this slide here I've got 3 linear equations in terms of the variables x1, x2, and x3. And each one of these equations actually defines a plane in 3-dimensional space. So I'm showing the 3 planes defined by these 3 different linear equations in this graph over here, which was created in MATLAB. So I've got an x1 axis, an x2 axis, and an x3 axis, and each equation is represented by a plane. Now, if there's a solution to these equations, meaning there is an x1 value and an x2 value and an x3 value that satisfies all 3 of these equations, makes all 3 of them true, then that actually corresponds to a point in this 3-dimensional space that corresponds to the intersection of all 3 planes. So that means all 3 planes are going to intersect here at one point. And when that is the case, we say this problem is well posed. Now that doesn't always have to be the case. Here the solution for these equations is given down here, and that is actually the point. So you can make a vector, put in x1 equals 1, x2 equals 2, and x3 equals 3, and it would point from the origin to that point right there, and that's the solution. Okay? Alright, so what if we have a different set of linear equations? Here I've got a different set of linear equations. I've plotted their planes here, and we see that all 3 of them intersect along a single line. So how many solutions are there now? Well, there's an infinite number of points along this line. So instead of just having one solution, one unique solution, there's an infinite number of solutions that satisfy these equations. Now this is what we call an ill-posed problem, or an ill-conditioned set of equations. Now there's also the case where you might have a set of equations that has no solution. So in this case that means the 3 planes that those equations define do not intersect, all 3 of them don't intersect uniquely at a given line or a given point. So there's actually no solution. No solution exists. So you will never be able to find an x1 value, an x2 value, and an x3 value that satisfies all 3 of these equations simultaneously. When you take and you formulate this set of equations as a matrix problem, the coefficient matrix will have a unique property called singular. It'll be a singular matrix. And we're going to talk about how to detect whether a set of equations is ill-conditioned or if it's singular. Singular means that it has no solution. Okay? So we'll talk about that in another video. So I just want to kind of give a broad overview of some common methods for solving AX equal B type matrix equations. This represents a linear set of equations where A is the coefficient matrix, X is the solution vector, B is the right hand side vector, or constant vector, or forcing vector. So how do we solve AX equals B? What are some matrix techniques? There are lots and lots of different kinds of matrix techniques for solving linear equations, but some of the more common ones are elimination methods. We're going to talk about Gaussian elimination and Gauss-Jordan elimination, and I'll make a video on each of these. And then there's also just finding the inverse. So if you find the inverse of a matrix, you can use it to find the solution to that set of matrix equations. So that's all I'm going to cover in this video, and we'll talk to you guys in another video and demo each one of these methods.